Tonight I will talk about the technology demonstration mission of SPATIUM-2 towards ionospheric TEC mission measurement. I am Necmi Cihan. I'm an assistant professor in Lausanne, QTech, and I'm the project manager for Kyushu satellite. In the last, this week, actually, we had the Lean Satellite workshop, and there we discussed about the on-orbit results of the Kyushu satellite, especially for the amateur radio frequency control segment. So Kyushu has two segments. It's like a two satellite in one structure. One part is controlled by amateur radio frequencies, and the other part is controlled by non-amateur radio frequency control. Part is called SPATIUM-2. And today I will talk about the technology demonstration towards the TEC measurements in ionosphere and chip scale atomic clock demonstration. For other parts of the objectives, actually we summarize all of them in the Lean Satellite workshop. So I'm really happy today that I will talk about this lot. So Kyushu actually has been developed as a collaboration between international academic institutions and private sector in Japan. And we collaborated in SPATIUM-2, especially for the utilization of networking and electron content measurements. And in the electron content measurements, the collaboration is done between Nanyang Technological University in Singapore and QTech. For SPATIUM project, SPATIUM-2 is a part of SPATIUM project, and it means Space Precise Atomic Timing Utility Mission. And the overall goal is to reach a technology readiness level and achieve a constellation of CubeSats to do 3D mapping of ionosphere. And in SPATIUM-1, actually, it was the first demonstration of chip-scale atomic clock in orbit. It was released from ISS in 2018. And on the right side, it is showing the on-orbit results for the chip-scale atomic clock, and it is showing for 10 megahertz clock output for count per second and the accumulated counter. In this mission, actually transmission was being done from the satellite side, and the calculations and processing were being done on the ground station side. But in SPATIUM-2, our objective is to make a technology demonstration by doing some onboard processing. Right now, we are doing something opposite. We are transmitting from the ground station, and we would like to show that inside the CubeSat, we can do some processing that at the end, we can calculate the time delay between the transmitted signal and the reception from the satellite. And also, we will continue one objective from SPATIUM-1 by monitoring the chip scale atomic clock on-orbit performance. And here it is showing what the part of the satellite that is occupied by the SPATIUM-2 boards. We are using 1 unit size. It's important because we developed 2U QTech standard-based system to show that we can support different types of payloads, and SPATIUM mission is unique because it is taking direct battery power, but we don't send any control from the bus system. It acts as a separate satellite. So we should be able to show onboard the modulation of UHF spread spectrum ranging signal from the ground station. And we should be able to derive the ranging signal time delay on board. And we will try to estimate TC values from this time delay we calculated. And this calculation will be done in the ground station side. But this is actually limited by the sampling frequency that we have 1 megahertz at the moment in the current configuration. And it's not so enough to make a scientific level TC calculations. But from technology demonstration perspective, it is very important. This is the actually photo is showing from the ISS deployment of Kyushu. It was in March 24, 2022. And we have 7.5 kilogram CubeSat, and it is actually SPATIUM boards, and the main bus and other missions are sharing a battery with a capacity of 74.5 watt hour. And Spatium actually regulates this power by itself, and it consumes approximately 2.5 watt-hour in orbit, and there is no ADCS requirement for Spatium missions. I will pass because of the time. Okay, for the TC demonstration mission, we are transmitting data from the ground spread spectrum signal from ground station at 450 megahertz. And from the satellite side, actually, it records this data and do the processing to calculate propagation delay time. For the time synchronization, we are using 1 PPS output from the GPS. But at the same time, the same recording is done on the ground station side with the same system, then it can do the same process by no delay time. So we can compare these two recordings to understand how much propagation delay time between reception on the ground or transmission on the ground, and also reception from satellites. To do this, one important thing to consider is things related to hardware error, and these are very hard to detect in the proof of concept. But we are using 1 PPS signal as an input for the RF switch, and when this RF switch is triggered by GPS output, it cuts the signal. Then we can detect actually when exactly 1 PPS output came, and we use this reference to detect when we receive a signal that what is in the UTC time. And this is how it looks like. Actually, the first one is showing this. We transmit the signal from the ground station, and we have two receivers. One is on the ground, one is in the satellite. Ground receiver receives it on immediately without time delay. But when we look at the satellite, it is with some time delay. But also when we have GPS signal input 1 PPS, it cuts off the signal in the recording. And when we detect it from the beginning of this gold code sequence, we can detect by comparison to the 1 PPS input. Then we can convert every beginning of gold code sequence to UTC time for comparison. And this is how the flight model looks like. We have Raspberry Pi CM3 for controlling the Lime SDR Mini. We are using this very small SDR for our recordings, and we have one GPS receiver for this mission, which is located on the top of the satellite. And we have this chip scale atomic clock from NTU, which also the clock source for the Lime SDR Mini. And these are some specifications for the hardware of the total electron content measurement board at the moment. And for this one, we are using the USB interface between these two boards. And other thing, we are using 1 megahertz sampling because of some computation limitations in the Raspberry Pi. And when we go above 1 megahertz, we detected we are missing some of the samples in the recording. That's why we limited it to 1 megahertz at the moment. And this is the GPS model we are using. On orbit, we were able to get GPS time output, but we were not successful to get the location data at the moment. And also for this calculations and inside the Raspberry Pi, we are using a Linux system, and it's able to run the GNU radio. Then when we use the GNU radio, our data output is the WAV files, and we are using this for the second phase of the process to detect the reception time. And actually recording looks like as in this figure. And when we transmit from the satellite ground station, there is no 1 PPS input to cut the signal off. But on the satellite side, when GPS is giving 1 PPS output for the timestamp, we see that this data is missing at this point. So we can understand this time for the calculation. And we have around RF switch has around 5 to 10 nanoseconds error. But however, GNSS 1 PPS output has around 50 to 100 nanoseconds error. And when the signal is cut, it is around 800 microseconds. So we did some end-to-end tests with the flight model at the beginning before delivered the satellite. Here is showing the amplitude signal that we received from the ground station, satellite SDR. And here you can see that actually when the 1 PPS output from GPS use the RF switch, so we can detect when PPS output came. And when we actually do the analysis, we were able to detect the RF switch repetitions for every 1 second intervals, and we did 30 seconds recording. And our processing actually get very good results for the RF switch detections, but also the standard deviation is approximately 140 microseconds. For calculations, it is high, but what we did actually, our output is also giving the wave signal around 1 PPS RF switch detections. So on the ground, we can make corrections if there is any calculation or detection mistake. So that's what we implemented as the backup. And also here on the right side, we are showing how it is detecting the gold code sequences. We transmit every 4 milliseconds. At 1 megahertz sampling, it shows 4,000 samples. So in first figure, it is showing it's detected every 4 milliseconds. So it is completely correct detection. But on the bottom, we are seeing like plus and minus 1 microseconds, which is actually error introduced by our sampling rate. So if we improve our sampling rate and processing capabilities, we can do this calculations or the detections in much better accuracy. And I will pass this one. For the current status, we were able to uplink spread spectrum, and we were able to confirm that SDR received it and demodulated it correctly. And onboard processing was able to detect the gold code sequence every 4 milliseconds as we planned. And GPS time output is collected, but the position data is not received correctly yet. We are still testing this. And 1 PPS output data is received, and it is under analysis to detect onboard accuracy, and we calculate the propagation delay. And also right now we are preparing for chip scale atomic clock monitoring mission. Right now we are able to detect spread spectrum uplink and the modulation works correctly, but some comments is the Raspberry Pi CM3 Plus with GNU radio and Linux operating system provided us so much flexibility in the development compared to any other MCU. But still, we are limited by hardware sampling frequency. Surely for the future, we need to go approximately, I think, around 300 megahertz sampling if we want to achieve 1 tech unit accuracy. And GPS receiver should be improved in the next version, and we can improve the current algorithm significantly as well. So this is my acknowledgement, and these are all my team members for the SPATIUM. Thank you very much.